Right now, in low Earth orbit, a 60-kilogram satellite is quietly running real AI workloads on an NVIDIA H100 chip. And this is just the opening move in a much stranger race than anyone expected. Google, Amazon-backed startups, an Italian quantum company, and even Elon Musk are all racing to build data centers that no longer sit in Virginia or Texas, but instead orbit the planet at thousands of miles an hour. And buried inside this race is a detail almost nobody is talking about. Classical computer chips, the kind powering your phone, your laptop, and nearly every server on Earth, are slamming into a wall in space that quantum computers might not have to face at all. If that sounds backwards, since quantum computers are usually described as fragile, finicky tech that barely survives inside a lab, you're about to find out why space might actually be the one place where the physics flips completely upside down. This isn't some distant theory being whispered about at a university conference. Working hardware is already in orbit right now. Billion-dollar valuations are already being handed to companies barely 2 years old. And the engineering choices being locked in this year will likely determine which approach wins out for decades to come. Let's start with why anyone wants to put a data center in orbit in the first place. Because the motivation is brutally simple: electricity. Global data center power consumption is expected to roughly double by the end of the decade, climbing toward nearly 1,000 terawatt hours. And in the United States alone, demand could exceed 100 gigawatts by 2035. On Earth, every watt of power that heats up these chips has to be pulled back out using massive amounts of water or air conditioning. In orbit, the math changes completely. Solar panels in space soak up nearly continuous sunlight, with no clouds, no nighttime, and no atmosphere blocking the rays, meaning a satellite can pull in dramatically more usable energy per square meter than an identical panel sitting on the ground. Elon Musk put it about as bluntly as possible when he announced his plan to merge SpaceX with his AI company xAI, specifically to chase this idea, simply saying that you're power-constrained on Earth, but space has the advantage of always being sunny. If a story about the world's biggest tech companies racing to leave the planet just to find enough electricity sounds like something you need to see for yourself, hit that like button and subscribe, because the details only get wilder from here. Google isn't bluffing on this either. Through a project called Suncatcher, in partnership with the satellite imaging company Planet, Google plans to launch 2 prototype satellites by early 2027, eventually envisioning massive clusters of 81 satellites linked together through laser-based optical connections spanning roughly a kilometer across. Early testing has already shown that Google's own AI-focused chips, called Trillium Generation TPUs, came through unharmed when blasted in a particle accelerator built to simulate radiation exposure. Meanwhile, a startup called StarCloud has already hit a real milestone, successfully running a version of Google's own Gemini AI model from a small satellite carrying an NVIDIA H100 chip, becoming, by most accounts, the world's first functioning AI data center in space. StarCloud is aiming even higher, projecting that a future orbital data center could eventually need as much as 5 gigawatts of electric power by 2035, an amount that would rival some of the biggest power plants currently running anywhere on Earth. But here's where the story stops being a simple tale of free solar power and starts getting genuinely complicated. Because space isn't actually the cooling paradise most people assume. On Earth, heat escapes a hot server through air conditioning and convection, air physically moving across the chip and carrying the warmth away. In the vacuum of space, there's no air at all, which means there's no convection whatsoever. The only way to shed heat in orbit is through radiation, essentially building large panels that glow the heat away into the blackness of space, the same way a campfire radiates warmth outward. Engineers on these projects have to design radiators with very specific surface areas, emissivity properties, and orientations, because a panel facing the wrong direction, say toward Earth instead of away from it, simply won't shed heat effectively at all. This single engineering constraint, dumping waste heat with no atmosphere to help, is quietly becoming one of the hardest problems standing between today's prototype satellites and a genuinely useful orbital data center. Now here's the part of the story almost nobody else is connecting, because classical chips and quantum chips experience this exact same brutal environment in completely opposite ways. A classical processor, the kind running inside every smartphone and every cloud server on Earth, generates an enormous amount of heat purely from the friction of electrons moving through silicon circuits at incredibly high speeds. That heat has to go somewhere, and in space, with no air to carry it off, engineers are forced to bolt on heavy radiator panels just to keep classical chips from literally cooking themselves to failure. Quantum computers, on the other hand, particularly the kind built with superconducting qubits, actually want to sit as close to absolute zero as physically possible. These chips typically run at temperatures around 20 millikelvin, a fraction of a degree above the coldest temperature theoretically possible in the entire universe, because even the tiniest thermal vibration is enough to destroy the delicate quantum states the chip depends on to function. If that doesn't surprise you yet, here's the twist. The deep vacuum of space sits at a natural background temperature of roughly minus 270 degrees Celsius, putting it remarkably close to the extreme cold that quantum chips already require here on Earth, using massive, expensive refrigeration equipment. Make sure you've already hit subscribe, because this next part is exactly why some researchers think quantum computing in space might be a far more natural pairing than anyone originally expected. An Italian startup called Rutonium is betting its entire existence on exactly this idea. Instead of building a traditional superconducting quantum chip that needs bulky cryogenic refrigerators to reach those extreme temperatures, Rutonium is developing what it calls a single photon qubit architecture, a quantum processor built entirely around particles of light rather than matter. Because the system runs on photons instead of cooled superconducting circuits, it can theoretically operate at room temperature. And according to the company's own engineers, photons are inherently more resistant to space radiation than traditional matter-based qubits. Rutonium's system is optical rather than electronic, which further cuts down how badly cosmic radiation can disrupt its operation, something that constantly threatens conventional silicon chips orbiting the planet. The company has explicitly said its long-term goal is building quantum computers small and rugged enough to embed directly inside satellites, drones, and robots, rather than housing them in some massive centralized facility the way Google or Microsoft might build a classical AI data center. This isn't just one scrappy startup chasing a science fiction dream either. The broader industry has started taking orbital quantum computing seriously enough to put real money behind it. Alongside Rutonium's space ambitions, separate efforts are already underway involving Red Hat and Axiom Space, who are testing a prototype orbital data center aboard the International Space Station, and Lone Star Data Holdings, which has already successfully flown an operational data center payload all the way to the surface of the moon aboard a lunar lander. None of these specific projects are running full-scale quantum processors yet, but the direction the entire industry is heading in is unmistakable. Infrastructure that used to live exclusively in terrestrial data centers is steadily migrating outward, first toward low orbit and eventually, according to some of these same companies, toward the moon itself. Here's where classical computing runs into a wall that quantum computing might genuinely sidestep entirely. Industry projections now talk about eventual gigawatt-scale data centers in orbit, each one requiring roughly 1 million AI-ready GPUs and solar arrays spanning an area equivalent to roughly 600 football fields. Every single one of those million GPUs generates heat that has to be radiated away using heavy, expensive thermal panels. And every single one of those chips has to survive constant bombardment from cosmic radiation that would gradually wear down and eventually destroy standard silicon circuitry over a period of years. Scientific American has reported that orbital hardware currently needs replacing every 5 to 6 years simply because of this radiation damage, an ongoing maintenance cost that doesn't exist in the same way for a data center sitting safely on the ground. Quantum systems built around photons, like the ones Rutonium is developing, are specifically engineered to be far more resistant to exactly this kind of radiation damage, precisely because particles of light aren't nearly as vulnerable to the energetic particle strikes that scramble traditional electronic circuits. The money chasing this idea has exploded almost overnight, and the numbers alone show how seriously investors are taking it. StarCloud, the same company that successfully ran Google's Gemini AI model on an orbiting NVIDIA chip, recently raised $170 million in a funding round that valued the company at an eye-watering $1.1 billion. For a company whose entire business plan depends on solving problems that have never been solved before at this scale, that kind of valuation isn't a small bet. It's a statement that some of the smartest money in the world believes orbital computing is close to becoming a real industry rather than a science project. StarCloud is reportedly seeking approval to eventually launch a constellation of as many as 1 million satellites, a number so large it would dwarf even China's previously proposed network of 200,000 satellites, a project Beijing has pursued partly as a strategic counterweight to American dominance in low Earth orbit. When a private American startup's ambitions start to exceed an entire national government's previously announced space program, you know the competitive temperature around this technology has shifted into something far more serious than experimental research. That competitive pressure is exactly why this is moving as fast as it is. Whoever solves the engineering puzzle first, cheap enough launches, reliable enough radiators, and chips tough enough to survive years of cosmic radiation effectively gets first claim over a layer of infrastructure that could end up underpinning a meaningful share of the world's future computing capacity. Nobody wants to be the company or the country left explaining years from now why they sat on the sidelines while a competitor quietly built out the orbital equivalent of the entire modern internet. That same dynamic, racing to lock in infrastructure before rivals do, is exactly what has pulled Google, Amazon-backed ventures, SpaceX, and a swarm of smaller startups into this race almost simultaneously over barely 18 months. There's also a brutal economic reality underneath all this excitement that nobody in the industry is shy about admitting out loud. An aerospace engineer at Varda Space Industries, who crunched the actual numbers on orbital data center economics, put it about as directly as anyone could, arguing that orbit has to win on cost or admit it's doing something else entirely. Google's own Suncatcher team has stated that launch costs would need to fall below $200 per kilogram by 2035 for their entire vision to make basic financial sense, a dramatic drop from where reusable rocket pricing sits today. That single number captures the whole tension driving this industry right now. The physics of solar power and radiative cooling genuinely favor space, but the brutal economics of strapping 1 million GPUs to a rocket still favor staying on the ground, at least for now. It's a tension that won't resolve itself through optimism or marketing alone. It will resolve itself purely through whoever manages to drive launch costs down fast enough to finally tip the equation in space's favor. There's another layer to this problem that rarely makes the headlines: the question of how these orbiting machines actually talk to each other and to Earth. A data center sitting in a building in Virginia can run fiber optic cable directly between racks, achieving latency measured in fractions of a millisecond. A satellite constellation has no such luxury. Engineers are betting heavily on free space optical links, essentially precisely aimed lasers beaming data directly between satellites with no physical cable needed, to connect these orbital clusters together and relay information back down to ground stations. Google's vision for Suncatcher specifically depends on this kind of laser-based intersatellite networking to link its planned 81 satellite clusters into something resembling a single coherent computer rather than 81 isolated machines spinning independently through space. If those laser links fail to deliver the bandwidth and reliability needed, the entire premise of treating a satellite swarm as one giant data center collapses back into a scattered collection of disconnected, far less useful individual machines. And when a chip in orbit gets struck by a high-energy cosmic ray, there's a real chance of what engineers call a single event effect, essentially a random bit flip somewhere inside the chip's memory or processing circuitry that can silently corrupt a calculation without any obvious warning sign. Over months and years of continuous exposure, this kind of damage builds up steadily, which is precisely why companies like StarCloud are already planning to swap out their orbital hardware every 5 to 6 years, rather than expecting it to last indefinitely, the way a ground-based server often can. Photonic quantum systems, the kind Rutonium and similar companies are betting on, sidestep a meaningful chunk of this specific risk, because information encoded in light particles is considerably harder for a stray cosmic ray to corrupt compared to information encoded in the electrical charge sitting inside a transistor. Supporters of orbital computing also point to an environmental argument that adds yet another layer to why this idea refuses to go away, despite the staggering engineering challenges. StarCloud has estimated that a fully solar-powered space data center could achieve roughly 10 times lower carbon emissions compared to an equivalent land-based facility, since it sidesteps fossil fuel-powered grid electricity entirely in favor of direct, unfiltered sunlight. For an industry under growing public pressure over its ballooning electricity and water consumption, that kind of sustainability pitch carries real weight with investors and regulators alike, even before a single gigawatt-scale orbital facility has actually been built. Whether that 10 times figure holds up once you factor in the genuinely enormous carbon cost of the rocket launches needed to get all that hardware into orbit in the first place remains a hotly contested question inside the industry, and not everyone is convinced the math works out as cleanly as the marketing suggests. Not every expert is convinced any of this happens on the timeline the loudest voices are promising either, and it's worth hearing directly from the skeptics. Industry analysts have pointed out that data centers, whether in space or on the ground, are extraordinarily complex systems requiring constant ongoing maintenance, something that becomes exponentially harder when the nearest qualified engineer is several hundred kilometers straight up, rather than a short drive away. Some researchers have gone as far as describing fully operational orbital data centers as potentially decades away, not years, cautioning that existing computing, storage, and networking technologies were simply never designed with orbital deployment in mind, and that retrofitting them for space introduces an entirely new category of failure modes nobody has fully mapped out yet. Even Carnegie Mellon researchers who specialize in putting computers on satellites have described some of the most aggressive public timelines floating around this industry as, in their own words, an optimistic interpretation of how quickly this technology can realistically mature. So what does the future actually look like once you put all these pieces together? Executives at companies like Microsoft and IBM are already describing a near future where quantum processors don't replace classical chips at all, but instead sit physically alongside them inside the very same data center, handing off specialized workloads back and forth between a CPU, a GPU, and a quantum processing unit working as one integrated system. One Microsoft executive described it by saying that a misconception many people used to have is that a quantum machine is a standalone entity, when in reality it's very much part of the broader computing ecosystem, sitting right next to everything else. If that hybrid model holds true here on Earth, it stands to reason the exact same logic eventually plays out in orbit as well. Classical chips handling the kind of brute force numerical computation they've always excelled at, while specialized, radiation-hardened quantum processors quietly handle the narrow category of problems they were uniquely built to solve, all while floating 200 miles above your head, soaking in continuous sunlight that never sets. It's also worth remembering just how recent all of this actually is. As recently as early 2025, NVIDIA's own CEO, Jensen Huang, was publicly downplaying quantum computing altogether, emphasizing how immature the technology remained compared to classical computing and casting real doubt on whether it was ready for practical use anytime soon. In the months that followed, Microsoft unveiled a topological qubit chip called Majorana. IBM began running quantum processors physically alongside classical supercomputers inside the same facility, and entire states like Maryland started pouring hundreds of millions of dollars into becoming what their own governor openly called the quantum capital of the world. The pace of change over just the last year and a half has been so fast that comments dismissing quantum computing as a distant curiosity already sound noticeably outdated. And that same accelerating momentum is exactly what's now spilling over into the conversation about orbital computing as well. Whether any of this becomes a genuinely practical industry within the next decade, or simply a wildly expensive science experiment that never quite escapes the gravity of its own launch costs, depends entirely on whether engineers can solve the radiator problem, the radiation problem, and the rocket pricing problem all at roughly the same time. What is undeniable is that some of the richest, most powerful technology companies on the planet, alongside scrappy startups nobody had heard of 2 years ago, are now spending real money betting that the answer to humanity's growing power and cooling crisis on Earth might genuinely be found by leaving Earth altogether. Whichever approach ultimately wins out, raw classical horsepower, delicate room temperature photonic qubits, or some hybrid combination nobody has even proposed publicly yet, the decisions being locked in across the next few launches will likely shape how the entire world computes for the rest of this century. If this video opened your eyes to a race happening literally above your head that almost nobody's covering clearly, that's exactly why this channel exists. So make sure you're subscribed with notifications turned on, because we'll be tracking every single satellite launch in this story as it happens. Thank you for watching, and we'll see you in the next video.